And welcome back. In this video, we're going to put together a number of the considerations of ozone that we've looked at in the past in SL as well as HL editions, where it's often used as a case study in resonance. Hopefully this will start to make some of those strange ozone questions that often turn up in exams that we saw make a bit more sense and put together all the information on how you might want to approach questions when dealing with ozone when it comes up. So the first thing with ozone is remembering its structure. It has a resonance structure where we have the 3 oxygen atoms that are bound. One with a double bond, one with a single bond, and then the charges that alternate between these atoms. This means that we have resonance. Okay, so our double bond can move as to which oxygen it is officially attached to. Okay. But when we see the resonance hybrid, what we notice is that we have 2 equal oxygen bond lengths. So the physical evidence that ozone has resonance is, of course, that the bond lengths are equal, not that of one double and one single. Meaning that the bonds are identical, but if we look at the octet rule, there has to be a double bond and a single bond. Of course, this leads us to resonance structures. Ozone's important to us in terms of society and chemistry in that it protects us from harmful UV radiation in the atmosphere. So the ozone layer is located in the lower stratosphere. Okay, so this is our stratosphere here. Oops. Okay, so we've got our stratosphere here. The ozone layer in the lower stratosphere before the troposphere absorbs huge amounts of UVC and UVB. Okay, so 90% of atmospheric ozone is in this area. Anything lower than this layer or this level is actually considered pollution because we do produce ozone during manufacturing processes down at the level of land. Okay, so we do get on the Earth's surface, we get some ozone production. Things like photocopiers, lightning, things like that produce ozone. The ozone absorbs UVC, UVB, and little to no UVA. So the UVA is what gets through our atmosphere and causes things like sunburn and warming and things like that. So what happens is if we have oxygen dissociation, the O2 is cleaved using UVC radiation and forms 2 oxygen radicals. Then, when we have O2 gas in the atmosphere reacting with an oxygen radical, we will get the formation of ozone. So this is the formation of ozone from oxygen in the upper atmosphere. The ozone then will absorb radiation, cleaving one of the bonds, forming O2 and an oxygen radical. That radiation is UVB that causes the cleavage of this bond, okay, which means that it is absorbed in the process of cleaving this bond and doesn't make it through the ozone layer. Essentially, ozone is an allotrope of oxygen. It's elemental because it's only made up of oxygen atoms, okay. It's a gas. It is polar because of the bent nature and the resonance structure. Generally blue in color, so we can use things like UV spectroscopy to measure the amount of ozone in the atmosphere. Has a strong odor and it's quite unstable. Okay, so this is our resonance structure here, and we can see if we look at these resonance structures, if we calculate the formal charge, we have a 0 plus 1 minus 1, minus 1 plus 1 and 0. So the resonance hybrid is between these. Noticing that this fits our formal charge rules in that the formal charges add up to cancel out, leaving the molecule ozone with no formal overall charge. It is a neutral molecule. Okay, so that should be the case. If we compare the photodissociation, i.e. the cleavage of the bonds due to light between oxygen and ozone, we can look at the different energies that are required. For the cleavage of the oxygen bond, double bond, in order to form 2 oxygen radicals, the wavelength, remembering that wavelength is the shorter the wavelength, the higher the energy. We have a 242 lambda wavelength of energy required. The wavelength required to cleave the bond in ozone to produce O2 and an oxygen radical is 300. The energy required is less. This makes sense if we look at the enthalpy of the bonds here, in that the bond enthalpy and therefore the strength of the bond is higher in the true double bonds that we see in oxygen versus 399 bond enthalpy, which is lower for the weaker bond that we see in ozone, remembering that it is somewhere between a double and a single due to the resonance. We have one sigma and one pi bond in the O2 molecule, remembering that it is a true covalent double bond. And then we have a sigma and 2 pi electrons delocalized over the 3 oxygen atoms in the O3 if we were to describe the bonding here, which means that it will be between a double and a single bond. The depletion of the ozone layer was something that was often talked about in the 80s and brought about huge amounts of worldwide action to combat the depletion, or what we saw as the hole in the ozone layer. Most of the ozone, as we mentioned before, in the atmosphere resides in the stratosphere. Anything in the troposphere and lower is due to pollution. Chlorofluorocarbons break down the ozone layer, allowing more sunlight through, heating the atmosphere, contributing to the enhanced greenhouse effect, and also increasing the amount of damaging UV that can increase the rates of skin cancer. Because of this increased UV radiation, and the hole in the ozone layer being considered an overall worldwide problem, the use of CFCs was reduced. CFCs were present in things such as refrigerants, air conditioning, and things like this. So the recycling of fridges and air conditioners was used, and other methods of refrigeration and gases to cause that were brought about worldwide. There is a natural mechanism for ozone depletion, this being that the oxygen free radical reacts with ozone, forming 2 oxygen molecules. We refer to this as photodissociation, and it occurs when harmful UV radiation is absorbed, breaking those bonds. The rate of reaction usually depends on the season, the time of day, and even the latitude and solar emissions. So this is highly dependent on weather conditions. Okay, how much of any particular radiation source is reaching the Earth, and then how much we're seeing in terms of temperature and otherwise changing these rates of reactions. Okay, so the photon of UV radiation has less energy or lower frequency than the one needed to break the double bonds in oxygen, so we see it cleaving ozone because those bonds are less strong. The ultraviolet photon necessary for this reaction has the same wavelength or required amount of energy to the radiation which causes sunburn and skin cancer, okay, which is why ozone being absorbing this radiation is critical. Anthropogenic effects on ozone are what we talk about in terms of the effects due to humans. These are caused by the release of chemicals which produce radicals, such as chlorine radicals that we see from the production of CFCs, but also nitrogen oxides, so the NOx gases that we see produced by the use of fossil fuels, nuclear explosions, and otherwise. Okay, these are increased by the amount of nitrogenous fertilizers used, explosives, and otherwise. The easiest one to control for this was CFCs, and in the 80s the production of CFCs was banned in many nations, but some industries still use them due to the fact that they have low fat flammability and they haven't found alternative sources. The use of CFCs is still monitored through monitoring air quality worldwide to ensure that we aren't seeing an increase or spike in CFCs that will contribute to greater depletion of the ozone layer. The key things that you need to look at in terms of catalytic depletion of CFCs, okay, is we have carbon with chlorines and fluorines attached. We have photodissociation of one of the carbon-chlorine bonds forming a chlorine radical. This chlorine radical will react with ozone, producing a ClO radical and oxygen gas. Unlike the natural depletion of ozone, where an oxygen radical is produced and will produce another molecule of ozone, this ClO radical can react with oxygen radicals that would usually produce ozone and now form another molecule of O2, producing a Cl radical. This means that overall we are seeing one oxygen radical plus an ozone producing two molecules of O2 and still having a Cl radical which can go on and proceed to continue this catalytic reaction, destroying ozone irreversibly to produce two molecules of oxygen. The problem with this is this regeneration of our Cl radical. CFCs and these chlorine radicals can persist in our atmosphere for 40 to 50,000 years, which means that they will continue to break down ozone for a protracted period of time, and there's nothing that is really removing them from our upper atmosphere. In the case of nitrous oxides, so our NO, this NO radical reacts with ozone to produce an NO2 radical and oxygen gas. The NO2 radical will then go on to react in a termination step with an oxygen radical, forming a new NO radical, which allows it to just go straight back and start reacting with more ozone in the atmosphere, plus O2. So overall, again, we are seeing the reaction of an oxygen radical plus an ozone to 2O2, and the radical that caused this is regenerated, which means that this breakdown of ozone will continue. It's catalytic. So the key reactions that you should know for this are NO2 radical goes to an NO radical plus oxygen. The NO radical reacts with ozone to form NO2 radical and O2. And then an NO2 radical can react with an oxygen radical to form O2. The net for all forms of ozone depletion is the formation of an oxygen radical with O3 forming 2O2, which is the same as the natural depletion of ozone in our atmosphere. The key thing is, for both the CFCs and the nitrogen oxide reactions, the radical coming from the pollution is regenerated, allowing the cycle to restart, which means as long as those pollutant radicals exist in our atmosphere, we see continual depletion of ozone without it being regenerated because we are using up the oxygen radicals that would typically generate ozone. Okay, that's it for ozone, and next up we will start to look at our hybridization.